Welcome everybody in the lecture hall, welcome everybody on Zoom, welcome everybody from the future. Today we are going to finish language models. It might be a shorter lecture because then we'll be done with the material of the lecture. And I emphasize that what we did with probabilistic retrieval and this is actually already normally on the master's level. So this is already quite advanced mathematics and advanced modeling. So I'm just going to go through the material. If we have time, we might also play with examples and ask you a few questions. So this is what we did last time, right? So perhaps the most important thing to understand, we talked about language models. The idea of a language model is that you take an input document and then you build a model that is able to generate new documents. There are many ways of doing that. Nowadays, ChatGPT and the like would be quite the standard. But there were models that already existed before that are also simpler. This is how it all started. And the idea, when we build these documents, is to do it with having in mind a deterministic automaton. It's the idea that if you do it the other way around, you consume words in order to check whether they belong to a language, right? Letter by letter. In our case, the letters are actually terms and the words are actually documents. So what we do is we consume term by term to check if a document is in a language. But we saw that it's possible to invert the automaton and make it work the other way around. It's like turning air conditioning into heating, right, with a heat pump. So the idea is that instead of consuming the terms to spit out a document, you do the opposite. You toss a coin and generate terms as you go. You toss a coin, you get a term, you toss a coin, you get a term. And this is how you get the sort of input you see in ChatGPT that word after word, it's all output. One of the simplest ways to look at it is with the chain rule. The chain rule is really step by step. You start, you haven't output anything. So the first coin that you toss is, will I output something or will I stop here, right? That's already a coin toss. That's the first 1 minus p stop. That's the probability that you are going to spit out something. The second in the chain is, given that you are now going to spit out something, what's the probability that it's going to be D1? In that case, D1 would be my first term, right? So that's a certain probability. It's part of my model, right? These are weights, basically. And so I multiply with the probability that my next term is going to be D1. Then again, the probability that I will spit out a second word, right? And then the probability that that second word is going to be D2, conditioned on the fact that the first one was D1. This is how you get the magic that the output actually makes sense, right? Because it takes into account what was output before. And then again, the probability, we are still not stopping here. And then the probability that the third term is going to be D3, conditioned on the first two, being D1 and D2. Then again, the probability that you still don't stop, there will be a fourth term. And then the probability that it's going to be D4, conditioned on D2 and D3. Why? This is about losing the memory of the past, right? We have what we call trigrams here. It means that we have the word we're outputting plus the first two, 3 in total, a window of 3. So at that point, since we're looking at a 3-gram, it's D2, D3, D4, but we lost D1. We forgot about it, right? This is called the Markov condition. Here is with 3 grams. And then the probability that we stop. Because if you interact with ChatGPT, you notice that at some point it stops. It just doesn't output forever, right? So then we stop. This is just the chain rule, and that tells you the probability that the document is going to be exactly in list semantics in that order, D1, D3, D1, D2, D3, D4. That is the probability. For whom does it make sense, this formula here, right? It's the chain rule. And we are making assumptions here, and that's the Markov condition. We are assuming that p stop is constant, right? It's always the same one, and so on. Okay. So again, I insist, this is the list semantics. The order is important, right? And this is using 3 grams. And in that case, I had an example with a length of 4. Now, there is a particular case that's actually quite interesting, at least theoretically, to study. It's the case of unigrams. Unigrams means that in your Markov condition, you forget everything. You even forgot the previous word. right? So you just spit out a new word, but it's a probability of its own, ignoring the past. Now, the formula is going to be simplified because the probability that the next word is going to be decay, conditioned on the previous ones, is the same as the probability that it's going to be decay ignoring the previous ones, right? That's an independence condition. It means that every new term is independent from the previous ones. And that we are going to assume that it only depends on the term. And it means that for each term, we have a probability that this is going to be the next term, right? So this is an example here where you have a probability distribution over the terms. This is what it is, a unigram model. It's just probability weights on each term that add up to 1. And that's an example where I simplified with just 6 terms, and there are weights, 1 for each term, adds up to 1. Okay, that's a unigram model. Okay. Now, you could imagine some sort of equivalent automaton that works like this, right? Where you have this 1 minus p stop every time, then multiplied by the weight of the next term. But now it's constant. It doesn't depend on the previous ones. Then at some point, you have the p stop, and you stop. Okay. So what is the probability here? Can anybody tell me, with the unigram model, list semantics, the probability that we are going to spit out exactly D1, D2, D3 in this order? Can anybody give me, using the chain rule, the probability? Given that what I give you is for D1, D2, D3, you have PD1, PD2, and PD3, right? So you have 3 numbers that correspond to D1, D2, and D3, right? PD1, PD2, PD3. What's the probability? You have p stop too, right? Yes? Do we have maybe going to increase the volume? See if it works.
Okay, I think it should be 1 minus p stop times the probability of D1 times 1 minus p stop times the probability of D2 times times 1 minus p stop times the probability of D3 times p stop.
Yep, exactly. That's exactly what it is. You got it right. And it's exactly in the pedagogical order, right? The idea that you don't stop, you output D1, you don't stop, you output D2, you don't stop, you output D3, and then you stop. Exactly. Right? That's exactly it. Who agrees with this? Okay. No, that's the unigram model because there's no conditions on the previous terms, right? It's totally independent.
You need to turn the volume.
Yes, thank you for reminding me. It's very annoying. It's white noise. Okay, so now I told you it's the list semantics. But there is something unique about the unigram model that wouldn't apply to other models like bigrams, 3grams, and so on. You couldn't do it. But for unigram models, there is something special. That something special is that we can migrate from the list semantics to the bag semantics. It means that we can compute, generally, we compute the probability of a document being some words in a specific order. But we could also switch to bag semantics and consider that the documents are not lists of words, but these are bags of words. It means that it's basically a vector where you have a number of occurrences, call them the term frequencies, right? It's the term frequency of each term in the document. And so we assume that a document is modeled that way, as a bag. Now, an interesting question is what's the link between the two? How do we go from the list semantics to the bag semantics? And the short answer is, well, you go from the list semantics to the bag semantics by forgetting about the order, right? That's the only difference. You forget about the order. What does it mean to forget about the order? It's basically the same as saying that 2 documents that have exactly the same words and in the same numbers, but in a different order, are in fact the same documents in the bag semantics. Who agrees with that, right? So if I tell you the polyban is working normally today, or if I tell you today the polyban normally working is, that's the same document in bag semantics, right? It's the same, exactly the same words. The order is different, but in the bag semantics, we don't care. So it means that in terms of probabilities, it's kind of a more coarse probability distribution, right? You have all your documents that are lists of words. Now we are going to merge these documents, put them in bag, and in the same bag, we put all of those that are the same but in a different order. What does it mean in terms of probability? It means that a specific document, the probability that a document is a specific bag of words, we sum over all possible orders, right? So we have the semantics according to list semantics, right? We have the probability according to list semantics, and we sum the probabilities of each specific ordering. If we sum over that, we get the total probability for this specific bag of words. Who agrees? Right? I have plenty of examples if you don't agree yet, so this is now coming. So in fact, that's a multinomial distribution. So who knows multinomial distributions? Binomial distributions? The Pascal triangle? Right? You've seen that, right? If you see like this is 1, 4, 6, 4, 1, that should be known to you. There's also 1, 3, 3, 1, 1, 2, 1. It's basically the weights when you have a plus b to the power of n, and you develop that, you get exactly these coefficients. It's the Pascal triangle. But now if you look at these terms, so I thought it would be fun to replace the terms with cats. So this is what I did. So here we have a document that has 4 times this cat. So let's call them Billy and Alfred, right? So this is Billy, and we have 4 occurrences of the cats. Now, in that case, there's only one possible order, right? Because it's indistinguishable. So it's just Billy, 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 right? Now we have here the case where in the bag, it's 1 time Alfred and 3 times Billy. So we have Alfred, Billy, 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 or Billy, Alfred, Billy, Billy, and so on. So these are all the possibilities. And you realize that there are 4 ways, 4 different orders for 1 time Alfred and 3 times Billy, right? Who agrees? Right? And then how many times if we have 2 of each? Twice Alfred and twice Billy. So these are the 6 possibilities, right? From a back semantics perspective, it's all the same. It's only different if you take the list semantics where the order is actually important. So we get 6 here. Now it's 3 times Alfred and 1 time Billy, and here 4 times Alfred, right? So 3, 1, and then 4, 0. Now you know the formula, right? Who already saw the formula n factorial divided by k factorial n minus k factorial? You know this one, right? Exactly, the Pascal triangle. So that's what I put in there, right? It's just exactly this formula here. Notice that the 2 numbers here sum up to the one here without the factorial, like 4 plus 0 is 4, 3 plus 1 is 4. Here you just put the number of occurrences in the factorial, you multiply them, and here is the total number factorial. Okay, so that would be the case of a unigram, length of 4, and how I would need to sum over the probabilities. Now, do you agree that the probability that we get this bag with twice Alfred and twice Billy is the sum of the probability for this, plus the probability for this, plus the probability for this, plus this, plus this, plus this? Who agrees? Right? Because it's disjoint, right? So if I sum over the probabilities that it's in these orders, then this is how I forget about the order, right? I put them together and I merge, right? So now here's another example where I have 3 different colors, right? So I have black, blue, and white. And in that case, that's where we have I should have written multinomial, that's no longer binomial. Now it's 1, 3, 1. Right? And then the formula generalizes to its 5 factorial, the total number, and then 1, 3, 1. So each one gets a factorial, and then you multiply. Okay? For whom is that clear? Right? So in that case, we would have 3 different words, and we want 1 occurrence of Alfred, 3 occurrences of Billy, and 1 occurrence of, I don't know how to call, let's call him Bob, right? One occurrence of Bob. All right, so now do you see that in the unigram model, how do we compute the probability of getting a specific document? Unigram model, list semantics, this is the formula you gave us, right? If I come back here, it's a product. You know that multiplication is commutative, right? So do you see that that number does not depend on the order in which you multiply? So it means that the probability of having D1, D2, D3 in this order is the same probability as having D3, D1, D2 in this order, right? So it means that in the unigram model, and that's only true in the unigram model, because of the commutativity of the multiplication, when I sum over the probabilities, these probabilities within the same packet are the same, right? This is probability of Alfred times probability of Alfred times probability of Billy times probability of Billy, right? So it's just a product, and it's the same product every time. So do you agree that to get the probability of the bag, it's the product times 6? Who agrees? Right? Because it's the same. So I just multiply with 6. I multiply with that. In the same way, here, that would be the same product every time because it's commutative. So it's this plus this plus this is basically the product done once multiplied with 20, right? So the more the combinations, the higher the coefficient is going to be. So the generic formula for multinomials is this one. You basically have all of your bins. So that's the term frequencies, technically. You have the product of the factorials of the term frequencies, just like we had 1, 3, 1 here. And then on the top, you have the factorial of the sum. That would be 5 here, right? So the numbers below, without the exclamation mark, they add up to the number above. That's how you recognize a multinomial definition. So that's the magic formula that gives you the size of the bag. So now, if you want the probability that you obtain a certain bag of words, it's basically this product of the 1 minus p stop times the probability of the term and so on, right? Multiplied with this coefficient. And by multiplying with the multinomial coefficient, we turn it into bag semantics. We forget about the order. That's the magic. Now, we are going to do it once with an example. So imagine that we now take the unigram model, the bag semantics, length of 4. I want documents of length 4. I want 2 terms. So this is here Alfred and Billy. 2/3 is the probability for Alfred. 1/3 is the probability for Billy. And here, this is my formula that I'm going to use. So you see on the right, that's my product. It's the probability of term T, but to the power of the number of times it appears, right? So the probability of getting Alfred is P Alfred times P Alfred. So it's P Alfred squared, right? So the square, this power of 2, that's basically the term frequency. It's the number of times that the term appears. Who agrees? Right? And then, so I multiply, this is all the probabilities that I multiply. It's basically the formula right here, but without the p stops. So this is the formula. And then I multiply with the multinomial term in order to get the bag semantics. Without that term, it would be the least semantics. If I add that factor, I should say factor, not term. Without that factor, it's the least semantics. If I add that factor, it's the bag semantics. I dropped the p stop, 1 minus p stop, p stop. Why? Because we see that it's a constant. So this is why we won't really care when we compute the scores. But in fact, one other way that I can justify dropping it is that I compute the probability, but conditioned on the length of 4. If I condition on the length of 4, then that's when I drop p stop, right? Because I know the length is 4. And if I want to remove that condition, then I would need to multiply with 1 minus p stop to the power of LD and then p stop. Okay? Who agrees with that formula? Who doesn't see it? Then I have pictures for you. So this is the example I gave you. 2/3 for Alfred, 1/3 for Billy. So now we have all these possibilities for bags, right? I don't care about the order, so I only put the possibilities of the bags we can have. So there's exactly 5 possibilities, and that's it. Let's compute the probabilities of generating these bags, knowing that at the end it should sum up to 1, right? I will have 5 numbers, they should sum up to 1. Remember that Alfred, the black cat, is produced with a probability of 2/3, and Billy, the white cat, is produced with a probability of 1/3. So what's the probability of the first one up there, the first document? What's its probability? The least semantics probability. Again, these are my values for keys, right? So what is the probability of the first document? Anybody? No? Oh, yes, over there.
1/3 to the power of 4.
Yep. So that's 1/81, right? What would be the probability of the second one? You can say? Yep. And so what would it mean in terms of fraction? So the fraction you get at the end? Anybody? Let me show you, right? So the first one is, so 1/3 to the power of 4, as you said. So this is 1/81. The second one is 2/3 times 1/3, 1/3 times 1/3. So you get 2/81. Then the third document, that's 2/3 times 2/3 times 1/3 times 1/3. So that's 4/81. The third document, it's 2/3 times 2/3 times 2/3. So 2/3 to the power of 3 times 1/3 to the power of 1. That's 8/81. And the fourth one is 2/3, 2/3, 2/3, 2/3. So 2/3 to the power of 4 gets you 16/81. Who agrees? Who sees that it doesn't sum up to 1? Why doesn't it sum up to 1? Yes? Exactly. Because this is the least semantics. So if we wanted it to sum up to 1, we would have to also count all the permutations, and then it would sum up to 1, right? Now, in order to make it sum up to 1, and because I care about back semantics, I need a correction factor. I basically need to, if I were to list the permutations, how many permutations would there be for the first one? Yes, I see 1, exactly. For the second one? You can show me with your finger if you want. Yes, 4. For the third one? Yes, 6, then 4, then 1. Yeah. So that's basically my binomial distribution correction. It basically means that for every one of these bags of words, that's the number of times they would repeat if I consider all the permutations, right? I would see once the first bag, 4 times because it can be in the first, second, third, or fourth position. 6 times I would see the third bag, 4 times the fourth bag, and 1 times the fifth bag. So now I need to multiply. That's what I get. Who sees that it sums up to 1 now? Right? 1 plus 8, that's 9, plus 24, that's 33, plus 32, that's 65, plus 16, that's 81. So we did it. That's an example of the distribution that you get for the specific case of the unigram model, back semantics, length of 4, and we have 2 terms, and the weights are 2/3 and 1/3. Could do the same, still for the unigram models and back semantics. If I give you more terms, if I give you other weights, who would be able to do it? Okay, a lot of raisins. Very good. There's nothing better than an example to actually see it. Okay, great. So this is why we get here, in the end, this formula right here, where we have the multinomial coefficient. So that's basically to account for all the permutations. Then we multiply, this was the 2/3 and the 1/3, that was the probability of the two cats. Then the power, that's the term frequency, the number of repetitions in our bag. And then we can add the 1 minus p stop and p stop. So now we basically also no longer condition on the order, but the order is unknown, right? Okay, so that is the generic formula for the unigram case, back semantics. If we have the probability weights pt, where t is the term, and we have p stop, and for a document that has the term frequencies indicated by tf, ld is the sum of the tfs, right? ld is just the length of the document. I could also have written sum of the tf over t instead of ld. Who is with me? Okay. So now let's get back to the k-grams. For the k-grams, you can no longer have the back semantics because it doesn't commute anymore. It doesn't commute. Well, multiplication still commutes, right? But the problem is that then the probability distribution is conditioned on the past. So if you move things around, that's going to change the weights because it's the condition is changing. So what happens if you have a bigram model? So a bigram model means that every word is produced conditioned on the one previous word. You forget everything before, but you look at the one previous word. So imagine that I have here a model. I didn't put everything, but let's say that we have a first case with the previous term being 2, and then you have the distribution on 2, B, and OR that are 0, 3, 0, 2, 0, 5, sums up to 1. Then we have the second case, BBB, that would be the previous term. Then again, we have a distribution on 2B and OR that sums up to 1. Then I didn't put it, there would be also for OR being the previous term and so on. Who has ever seen a Bayesian network? Because that's actually a node in a Bayesian network, if you actually look at it. Because you have, it's a probability table that is conditioned on the previous term. So you have a probability distribution, but for every possibility of the previous term. Who is with me? Okay. When you look at Bayesian networks later, I'm sure you will see them, causal models, causal inference, and so on. Then have that in mind. This is basically very similar. Okay. So now in the bigram case, what's going to happen is that when we multiply, we will not just have the PD1, PD2, PD3. Now we have the probability of a specific k-gram. D2 is the new one, but it also depends on the previous one, right? So this is this table right here. That would be that D1 would be looked up here, and D2 would be looked up here. And then again, we have D2, D3. It's again the bigram. So this is the probability of producing term D3, knowing that the previous term was D2, right? And you still have this 1 minus P stop and P stop in exactly the same way. Are you still with me? Right? It's becoming complex now, right? Okay. But now, of course, the question is, how do we get an information retrieval system with that, right? And there is a trick. It's a thought experiment. It's a little bit like the elves in Antarctica that we used last time. Here's the thought experiment. Imagine that I'm using my Antarctica facility, and I ask my little elves to build a model for every document in my collection. So if I have 1 billion documents, then I'm going to have 1 billion models, right? So my little elves are going to build these billion models. They get this automata, right? They put the weights in there that came from the documents. And now they have the model ready to function, right? So I could even ask them to start producing new documents, right? You just put as an input, you take a document in the collection, so a document that already exists, right? And you take the corresponding model, and then you generate a new document that is an imitation of the one you selected, right? A new one, but based on the internals of the previous documents. In fact, it's quite fun to do it in reality. This was way before ChatGPT. That was already like 20 years ago, 30 years ago, you already had that, right? It's based on what I explained to you today, the very simple case of k-grams. And I showed you an example here. It's taken from from a book where they actually showed that example with 1 gram, 2 grams, 3 grams, and 4 grams. So the first one is you forget about the past. You don't even know the previous words. So you get something like to him swallowed confers here both, which of save on trail for RA device and road life have. He late speaks, or a more to less first you enter. That doesn't mean anything, right? And you feel that the words are kind of random and there is no logic and no attachment between two words that follow each other. Now, what if we produce a document? So the training set, by the way, I didn't say it's taken from Shakespeare, right? We just trained on Shakespeare, the complete works, and then get that. So now imagine that with Shakespeare's, we computed this table right here now with bigraphs. So we only care about the previous word. And then we get, why does stand forth thy canopy forsooth? He is this papable heed the king Henry, leave king follow. What means, sir, I confess she, then all sorts he is stream captain. So now it kind of starts looking a little bit like, that sounds like something, right? That's because now when you have a window of two words, they are kind of making sense together, right? That's called the collocation in English. Okay. Then 3 grams. It means that you look at 2 words before. Fly and will read me this news of price. Therefore, the sadness of parting, as they say, it is done. This shall forbid it should be branded if renown made it empty. Now you're getting better, right? That starts sounding more and more natural. And then the 4 gram, 3 words before, King Henry, what I will go seek the traitor Gloucester, extend some of the watch, a great banquet served in, it cannot be but so, right? So of course we still don't have ChatGPT, but it still starts to be impressive with windows of 4 and 5. Now, this is not a large language model lecture. ChatGPT is much more evolved in terms of what happens in there. If I quickly summarized, I'm also not a big expert of that, but basically what ChatGPT does is that it doesn't only look at the previous world, it also looks at the future world. It basically look at the context that there is around every world, and that's called attention. So it's a much more complex model, and the difference is also the scale. This is why it's called large language model. Like they trained on the whole Wikipedia, the whole internet, right? The other thing that's relevant connecting to ChatGPT, do you remember the vector databases that I told you about when we have the scalar products in the vector space? Well, it turns out that in LLMs, you also have the vector spaces and the inner products, but not in the same way. What we did with the vector space is that we had the bag of word model, and every vector carries the term frequencies or the TF-IDFs of the words. In ChatGPT, you don't put the same things in the vectors. You basically, it's called the word embedding, where every word, based on the context in which it appears, is abstracted away as a vector, and every word belongs to a vector space. And then you can look at the proximity of the words with each other. But it's much more difficult to interpret than the bag of words and the TF-IDFs, right? It's much more abstract than this. Okay, by the way, there's an LLM lecture at ETH. So if any of you want to go deeper into specifically LLMs and ChatGPT, then you can do that, right? But what I wanted to show you here is that this is the sort of things you can do very quickly. You can take your laptop in one afternoon, you can actually do it. You can do it on Sherlock Holmes or whatever you want. And it's quite easy to do, actually. And I actually played, so now, of course, there's the more modern version. And I did an experiment back then, so that was ChatGPT 3.5. And so I asked ChatGPT, wo redet man Weltschweizerdeutsch, right? And actually, you can see it got it wrong. Weltschweizerdeutsch wird hauptsächlich in der Romandie gesprochen, der französischsprachigen Region der Schweiz. Diese Region umfasst die Kantone Genf, Waadt, Freiburg, Neuenburg, Jura und Teile von Bern und Wallis. In diesen Gebieten wird Weltschweizerdeutsch, so it understands Weltschweizerdeutsch, Weltschweizerdeutsch, als Dialekt des Französischen gesprochen. That's of course not correct. Der jedoch einige Unterschiede zum Standard Französisch aufweist. Weltschweizerdeutsch wird auch von einigen Deutschschweizern gesprochen. Wer spricht Weltschweizerdeutsch hier? That's not very correct. Die in der Romandie leben oder arbeiten. ChatGPT 4 got it right. It actually caught the incorrectness of what I was asking for here. Weltschweizerdeutsch oder Weltschweizerdeutsch ist eigentlich kein offizieller Dialekt oder eine Sprache, die in der Schweiz oder anderswo gesprochen wird. Es scheint eine Mischung aus Welsch- und Schweizerdeutsch zu sein, die zwei verschiedene Dinge repräsentieren. It's impressive, right? ChatGPT 4. Welsch bezieht sich normalerweise auf die französischsprachige Region in der Schweiz, die auch als Romandie bezeichnet wird. In dieser Region sprechen die Menschen Französisch und verschiedene lokale Dialekte des Französischen. Schweizerdeutsch hingegen ist eine Gruppe von Dialekten, die in der deutschsprachigen Region der Schweiz gesprochen werden. Schweizerdeutsch unterscheidet sich von Standarddeutsch und wird hauptsächlich in gesprochener Form verwendet, während Standarddeutsch in offiziellen und schriftlichen Kontexten verwendet wird. Doesn't call it Hochdeutsch, but da Weltschweizerdeutsch eine Kombination der beiden Begriffe zu sein scheint, ist es keine tatsächliche Sprache oder ein Dialekt, der in der Schweiz gesprochen wird. You see the power of ChatGPT that it manages to actually catch this, right? Just to explain, I'm assuming a lot of you understand German. What it's basically saying here is that there is a dialect in the French-speaking Switzerland that people speak, and that is a variant of Swiss German, which is of course not correct. But in ChatGPT 4, it actually notices that this is the word would hint that it would be a Swiss German dialect, but in fact they do speak French in French-speaking Switzerland. So it got it. And I was very disappointed because ChatGPT 4.0 gets it wrong again. So I don't know what happened, but now if you look, this is, I'm putting directly in English. So here it basically fell back to the previous one. Yeah. What I want to say here is critical thinking, right? ChatGPT is like a calculator. It can make mistakes just like calculators can overflow. So you always have to double check anything that is output by this. In my other course, we didn't manage to do it for information retrieval, but I have another course, big data for engineers. And here, ETH actually trains on the textbook, and there is a chatbot called Ethel that is available on ETH and EPFL under ETH and EPFL's control. And here, the students can actually directly chat and ask questions about the textbook. I think there are 6 courses at ETH that use the chatbots. For information retrieval, I asked for permission, but I didn't get any answer from the licensing team of the book. I assume maybe they don't have any licensing model for this kind of things, right? But anyway, I just wanted to have this parenthesis because it's kind of interesting to look at the evolution of things compared to how it were before. But if now I come back to building an information retrieval system, not ChatGPT, something really simpler, here's my thought experiments. The user is sitting in front of their laptop and they type something, a query, Q. Q is a list of words, so let's assume the list of words. Now the model is this. Imagine that my elves in Antarctica, still them, they picked a document at random, right? One of the billion documents in my collection, the real ones. They pick it at random, they take the corresponding model, and then they use that model in order to generate this new document. And it turned out that that document was Q. That's an enormous luck, right? It's like, what are the odds of that? It's a probability of 0.00000, probably lots of zeros, 1, right? But let's assume that this miracle happens. By chance, they picked a document at random, picked the model, generated a new document, hitting the button, and it turns out to be Q. And the question I'm asking, given that they by chance produced Q, which one of the documents on the collection, the initial collection, was the most likely that they actually picked when they picked it at random? Who understands that thought experiment? It's a little bit like the weather and the umbrella, right? I tell you, oh, by chance, today I have my umbrella. So what are the odds that it's raining? It's the same here. I'm telling you, by chance, they generated query Q. What are the odds? What is the most likely documents that they actually picked that by chance produced query Q? So in fact, the idea is this, right? You take the document, you generate a model, happen to generate the query, and you ask yourself, what is the most likely document that could possibly have by chance generated that query? Now you know that if I ask the question in this way, it's very difficult to answer, right? How could I even tell you which is the most likely document? But you know the magic of the Bayes formula and the Bayesian reasoning. So I'm asking for the probability that it was document small d, given that it produced a document small q through the model. Well, let me swap the two sides using the Bayes formalism. So now I end up with the probability of producing a query, producing a document small q, given that I picked document small d, with the two correcting factors of the Bayes formula, right? I multiply with the probability that it's d and divide that by the probability that it's q. Now, if we can compute what's on the right, then we get the probability that basically the score of document D. And I said score because in fact we can use this as a score in an information retrieval system. Because then I could return to you the documents. So D, I could do it with E, F, G, all kinds of other documents, always conditioned on Q. Who agrees that if I take it as a score and I return to you the highest scoring documents that have this highest likelihood, it's likely to actually be a good engine. Who understands the intuition here? Right? I return to you the most likely, the closest documents that are the most likely to have produced query Q. So we need to compute that, and I have my little elves to do that, so they can compute that for every document in the collection, right? But there's a few tricks, right? Because I can technically, so we need to sort by this. This I can actually drop because that's a constant. It's Q, right? It's the query. So that I can drop. I don't need to always divide by this. This is not going to change the order. Who agrees? Yes? So that I can drop. This I can drop. It's actually not a trivial question. In Bayesian reasoning, that's called a prior. That's my prior probability on the documents. It's actually very tricky, and people can discuss that for hours. What is the prior that you should feed into Bayesian reasoning? By default, we kind of put the uniform distribution and that's it, right? So prior to knowing that by chance you output query Q, you would just assume, okay, we picked it randomly from the collection, so it's uniform. So you might argue, right? But let's assume that the prior probability for document D was actually just uniform. Then it means it's a constant. It's 1 over the number of documents, so I can also drop it. So I'm basically just left with that. But do you see that this we already know? Because it's the probability given a specific model, which came from a document, given a model, what's the probability of generating document Q? That's basically, in the case of the unigram model, for example, that's this formula right here. Who agrees with that? If I feed in that the TFD TD, so that would be TFTQ now, I just feed in that the term frequencies of my query, that gives me the probability of generating it. Of course, in the case of the list of words and bigrams, 3 grams, then that wouldn't be this formula, right? Then it would be the more complex one, this one. Okay, let me get back to this. I still have a rabbit to get out of the hat before the break. So that's my formula. I'm assuming the unigram model in here. In fact, the unigram model is actually already quite useful. It doesn't give you ChatGPT-like results, but still. Let's look at that. So that would be our score, right? Look how I was careful in the way I put D or Q, right? Because we compute the probability of generating document Q. So when I multiply my PT, the powers should depend on Q, right? It's Q that I'm generating. So, and the same here, the bag of words, when I forget the order, it's all based on Q, right? So there's only Q in here. Where is D then? D gave me the weights. I basically looked at document D and inferred the weights. So that's, in fact, the weight is basically, I could take the term frequency divided by the length of the document, right? The higher the term frequency, the higher the probability, and the lower the term frequency, the lower the probability. So I basically compute my weights based on the input documents. So now you see it's the term frequency of document D. Now, note that Q is constant, right? There's a lot of constants in there. But in fact, I would like to first turn it into a sum. Why? You probably see it coming, right? I love to turn products into sums. I already did it last week for probabilistic information retrieval. How do I turn a product into a sum? On Zoom, maybe? How do I turn products into sums? What's the magic? Yes? With the log, exactly. So let's take the log, exactly, somebody on Zoom as well. So we take the log. Now I turn all of that into sums. Now, what can I get rid of? Everything that doesn't depend on D. So that doesn't depend on D. So that's a constant. I can throw it away. That's also a constant. I can throw it away. So I'm basically left with this, right? So let me put the constant C. And now is the aha moment. Look at what we got. We have a sum over the terms of a product of a number that came from the query side and a number that came from the document side. Who sees that it's a scalar product between vectors? It's a scalar product between a query vector and a document vector, where the query vector has term frequencies, no IDFs, just the term frequencies, and the document vector has the log of the term frequencies, plus a constant. Who feels like, aha, right? That's wow. What we have just discovered now is that by using this trick, the third experiment with the language model and generating by chance a query queue and with the unigram model, back semantics and so on, I happen to find a score that is the scalar product of 2 vectors. So I just found the justification of why the term frequencies make sense. Just like if somebody asks you why IDF, why inverted document frequencies, well, you can say, oh, that's because of probabilistic information retrieval, right? If you use the base formula like we did 2 weeks ago. And if somebody asks you why the term frequencies, oh, but you can say that's because of the language models. Because when we assume that we by chance produce a query queue with a language model, we get it. That again gives that. So you see, it seems like no matter where you go and you try to figure out new methods of building systems, you always end up computing a scalar product between a query vector and a document vector, right? And by the way, on the document side, we have a log. That is the reason why in this menu that I gave you, the smart menu, there is a variant with the log of the term frequency. That's why. That's precisely for that case. So you would take for Q, the term frequency, and for D, the log of the term frequency. Right? Who is with me? Okay. So basically, we have a justification for term frequencies from language models, for inverted document frequency for probabilistic model, and as a whole for the vector space model, because the scores are just scalar products between query vectors and document vectors. If we put the two together, we can actually motivate the TF-IDFs. In reality, for the probabilities on the document side, we smooth a little bit. That's what I explained last time, right? If we just take the term frequencies of a document, it might be a bit biased, and we are not going to cover everything. So it means that we add, instead of just taking TF over L, TF over the length, we add a little bit of a correcting factor. And for that, we actually use the collection frequency. Like we look at the entire library, the entire collection, and we add a corrected term that smoothes it a little bit like this, right? That basically removes the local biases. Okay. So basically, that's what we covered. There are other people who do it this way, who use the other way around. They take the query, generate a model for the query, and compute the probability you would take a document. You would know how to do it. It's exactly what we did the other way around. I'm not going through it. And then there are people who do it differently. They generate a model for the query. They also generate models from all documents, and then they compute the distance between the models. How come you compute a distance between the models? There exist distances between probability weights. That exists, right? There's plenty of them. One trick, for example, you could use the L1 norm, right? You sum over the difference of the probabilities for every possible small omega and add a constant to renormalize. But I'm not going into this. I just want to tell you that exists, right? So there are all of these approaches. Which brings us to the break. I'm actually done with the slides. After the break, I will just give you a few problems to solve, just to train on the Bayesian reasoning and the language models, and then I will let you go, right? This is it. We've done all the material of the entire semester, right? Bachelor's level plus probabilistic language models. So there will be nothing more. Next week, we'll have a quiz, a game. I will wrap up a little bit. So let's take a break. I will see you in 15 minutes, right? So see you later.